be a new topic for you to understand this. So that's why you can just start the lectures as soon as possible, so that you'll be having a much time for your solution for solving the graded assignments, or because I guess week
Yeah.
10 and 11 both are having the deadline as 21st.
And 21st August.
Yeah, yeah. Okay, and after that we'll start revision session and all. So try to wrap it up. Just go through the lectures. I'll give you a brief idea about the whole week of week 10 today. Maybe whatever will be left, we'll be discussing the next lecture, but we'll try to wrap it up.
Yes,
Okay,
yes.
and whatever I'll give you an idea that will be sufficient for your understanding for whole week. Okay, so I'll just give you the summary for those things. So we'll start with the graph. Those things which are very basic, I'll not be taking much time. So I hope that will be fine for you. Are you able to see my screen?
No, no, sir. No, 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 sir.
Okay, no. Okay.
Yes, the screen is visible now.
Visual, yeah.
Can you see my screen now? It feels right. Okay.
Yes, sir.
My
Yes, sir.
voice is
Visual.
audible.
Yeah,
Voice is
proper
audible.
voice is audible. Everything
Yes,
is
sir.
proper, sir.
Okay.
Hello, sir.
Yeah, yeah.
Sir, actually, I have one doubt. Sir, actually, I qualified this qualifier exam in like on last like 7th August, 7th
Okay.
July,
Mm-hmm.
but I have not got
So,
email ID.
Even term 1 के बाद मिलेगा आपको.
Okay, okay, okay,
In
okay,
September, you will get the ID and ID card also.
Yeah.
okay,
Term 1 के
okay.
बाद.
okay.
Sir, I have one more doubt, like just a small doubt. What could be the possible syllabus for this inter?
Yeah, in terms the whole syllabus will be coming 1 to 12 weeks, but the major portion will be from week last 3 weeks. Like because we have for Maths1 we have just 11 weeks, so last 3 weeks will be having a good amount of portion. You can
Okay,
just
Yeah,
think
50
of
to
as
60%.
yeah, more than that, yeah, 50 to 60% of that questions will be from the last 3 weeks, week 9, 10,
okay,
11. Okay,
okay,
and the other 50 you can just think of as one question each from your whole week, from week 1 to 8, and then the remaining questions. If you have some 16 questions, half of the questions will be from last 3 weeks.
okay,
Okay.
okay. Thank you, sir.
Yeah,
Thank
you
you,
can
sir.
think. Okay. So we'll start with the graph. These are just the basic things. I'll just go through this very fastly. Whenever I guess we'll be dealing with graph coloring, vertex cover, independent set, adjacency matrix, BFS, DFS, DAG, and then topological sorting is there. So all those things, I guess if somebody has went through the lectures, would have at least known the topics at least. If you haven't
Yeah.
understood in a great way, you would have known the topics at least. Okay, so these are some of the topics that you should be knowing after this session most probably. Okay, so the graph is it's like many a times we represent mathematical. It's like basically a mathematical structure only that is used for a pairwise relationship. You can be given in CS and all. You generally use the graph. Many of the algorithm is done mostly on the graph theory. Okay, so here we'll just get an idea about what is that graph theory, and some of the algo also will learn like BFS, DFS will be learning, and in the next week we'll be learning some of the others algo also. Okay, so till now in this week we'll just be dealing with the unweighted graph, any graph that doesn't have any weight. So we'll just be having a image that will be okay. I'll just start with that. So basically, a graph is basically presented as some vertex. If we are just building one graph, there must be some vertices that will be joining. Okay, let's for example, there is a graph this A, B, C, and D. Okay, and you're just joining it. This is just a very basic, simple graph where you just have four vertices and four edges are there. Okay, so we can just think of as A as a one vertices, and this is how you present generally we represent a graph as first is a vertex. Z is basically a graph G, that is this you can just think of, and you have a vertices. You have a pair of vertices. Basically, there are four vertices, and you have a edge also. Okay, So here you can just think of as A, B, C, D are the four vertices for this graph G. And you can say that edges are what AB is one edge, and then BD is the other edge, and CD is the others, and AC is the edge. Okay, there are basically four edges, four vertices. It's a very simple graph. Okay, and this is how you present a graph. Okay, you can have an end, like you'll be going through a different difficult graphs also in the meanwhile. But as of now, it's just the one of the simplest graph that you can have. Edge is basically the, if you're just joining two vertices, you are getting some sort of a edge, and that is basically your edge. And what happens, you in this is an undirected graph also. If you just think of this is a simple graph, and it's undirected also because I didn't give any direction to any, right? It's basically, if you have, okay, I'll just uh, uh, so the graph I have already defined is pretty simple. Then if we'll just go through the types of a graph. So in the types of a graph, basically you have a two types of a graph. One is a directed one, and the other is the undirected. Okay. So in the directed graph, so whenever you are representing a graph is basically a representation of some sort of a relation that has been defined earlier. Okay, in the lecture, sir was defining, like, if there is a collection of teacher and then other subjects that they're teaching. Okay, so there can be some sort of a relation, like a teacher A teaches maths, and teacher B teaches some science or social studies. All those can be a relation, and that can be represented in a form of a graph also. Okay, so whenever you are representing a sort of a relation on a form of a graph, you can have a sort of directed graph and an undirected graph. Okay, so in the directed graph, let's, for example, here it has been represented. One very basic example, like there is a two ways and two vertices for this simple graph, or you can think of as a relation where you have a is a sum city. So you can just think of as a graph can be represented for this interpretation, like A is some city and B is some city. Okay, you have a flight from A to B, but there is no flight from B to A. Okay, so this is how it has been represented. Like there's a relation that A, you can go from A to B via flight, but there is no flight from B to A. So that is how it has been represented, and this is what you mean as a directed graph, because you just have a direction from A to B. You don't have a direction from B to A. Okay, are you getting this point?
Yes, sir. Yes.
Yeah. Okay. And if I'll just represent this like A and B, so both are city, and if I'll represent like this, okay, like you have a flight from A to B and then B to A also. If both the relation exists, then you can say that this graph that has I have represented AB with both the direction is undirected graph, and you can represent this as like this also. Okay, so this is also a same undirected graph. Basically, for you have basically you can go from A to B and then from B to A also. This is how you represent the undirected graph. So both of them are correct. Okay, is this clear till now?
Yes, sir. It's clear.
Yes, sir.
Yes, sir.
Yeah. So for any graph, let's, for example, you have this. This is also an undirected graph, because you can see that for we can if let's, for example, you're just representing this as a some city ABC, and then there's a route.
Hello.
Excuse me, sir.
Yes, sir.
Hello.
Hello. Yes, sir.
Hello. Yes.
Sir,
Better
you are
speaking.
not clear.
Yeah, hello.
Screen is also not.
Is the teacher still here, or did they leave or something? Hello, sir.
Don't worry, he will be back soon.
Instructor is still here. I think the host is here. The
Yeah.
co-host is here, but
Yeah, can you hear me now? I guess I
Yes,
lost
sir.
the
yes,
connection.
sir.
Yes, sir.
Yes.
Okay. Okay, 1 second.
Hello.
Yeah, so okay. 1 second. Just because I'm not able to. Yeah. Yeah, if you were somebody was asking something.
Sir, your screen is not visible.
Okay, it's fine. Just wait for 2 minutes. Yeah, so till now, what I was discussing about in 2 minutes, I'll be sharing the screen because I've not been made the course. So, what I was what I was saying is you can be given any relation can be represented in a form of a graph, okay, and that graph can be a undirected or a directed graph. So, one example that we were dealing with, like there was a very simple two cities were there, and there was city A and a B. If you have a flight, just a flight from A to B, that's it. That means you're having putting like you can go from A to B, but you can't come to B to A via flight. Okay, so that basically is a directed graph. And if you have a like a way from A to B and then from B to A also, then you directly say it as a both arrow are present there, right? It's basically an
Your screen
undirected
is
graph.
not visible.
No, it's fine.
Yes, sir. Your screen is not visible.
Sir, your screen is not visible.
Yes, sir. Now it's visible.
Is it visible now?
Yes, sir. Yes, sir.
Okay.
Yes,
So
sir.
I was just saying about the directed and the undirected graph. I guess this is clear. This was very simple. So I gave you an example, right? So can somebody tell me whether this graph that I have given? So let's think of as a relation where some three cities have been given to you, and then you can have a flight from B to C, from C to A, like both paths is available, and from B to A also both paths are available. What can you say about this? Graph, whether it's a directed or undirected graph. It's a mix, right? But what do you say that? See, for any graph that has been represented, if any even one that edge that you are seeing that is a directed, then the whole plot will become a directed graph. Okay, so for becoming an undirected graph, each and every edge should be like bidirectional. Okay, are you able to understand that?
Yes, sir. Yes, sir.
Yes, sir. Yes.
Okay. Yeah, so this was simple. So that is what I had written here. If V dash is some V and V dash is a edge, vertex, and that belongs to the edge. Like V dash is a basically a edge in your graph. Okay, and so V dash V is also should also be there. Okay, then only you can say that it's an undirected graph. That means what? If you, I'll just in a layman language, if you just think of if you can go from C to A or A to C both, then you can say that it's a undirected. Like for each of the edges, whatever the edges present in your graph, okay, then if all of them are like this, then you can say that it's an undirected graph. Okay, and if any one, even you're able to find a single that is not a bidirectional, you can say that the whole graph itself is a directed graph. Okay, is this clear? But
Hello,
nobody is
sir.
going to ask you. Yeah.
Hello, sir.
Yeah,
Sir,
yeah.
what is the V dash?
Just the two. Say, how do you make an edge? Basically, there should be two vertex, right? That will. So edge is basically simple, right? So if you are defining an edge, how do you define an edge? There should be connection from one vertex to the second vertex, right? So V dash
Yes.
you can just think of as a one vertex and the other vertex, right? So there's a connection from V to V dash. Okay, so you can move it from V to V dash. Okay, if you are moving from V to V dash, okay, that becomes one edge. So you have should be there must be a connection from V dash to V. Okay, that should also belongs to your edge for that graph. Okay, and if this is happening for each and every edges, then you can say that your graph is undirected. Okay, that is what I have defined here. Like for
Okay.
each plot, like for example,
Okay.
this was represented like this. That means you can go from A to B and B to A. And this is like if A if A comma B belongs to your edge, B A also belongs to your edge, right? Correct. So you can go from A to B and similarly from B to A also. And this is happening for each and every edges. Then you can say that's a undirected graph.
Okay, sir.
Okay, that's basically a bidirectional, and this is like you can just go from one direction. There's some fixed direction here. Okay, but here both directions are possible. Now the next thing is the path. Path is basically simple. Path is just the sequence of the edges. Yeah. You're asking something.
The previous graph that you made, where only from B to C, there was an H. Yeah. So that one was directed, right?
No, so only this edge is a directed, but if we'll talk about the whole graph, is a basically the directed graph itself. Because even if you're just getting one edge, that is a directed edge. Okay, you can say that the whole plot itself is a graph, directed graph. For undirected graph, each and every edges that you are present should be bidirectional. Okay, even if you are finding one direction, like one unidirectional edge, then the whole graph will be a directed one. Okay, because you already know that. See, if you are representing something like this, if it is been represented like this, that means both each of the edges are bidirectional, right? Correct? Well, this is a both are bidirectional. But even if you are getting one edge that is unidirectional, then you can say that the whole plot itself is a directed graph. Okay? I hope this is clear. Yeah. So, and path and all is like pretty simple. Path is basically it's a sequence of edges. If you are just going from one vertices to some distant vertices, okay, you'll be going through some you'll be using some 2-3 edges, right? So that basically is a path. The one thing that you should be remembering and in the path is like you should not be repeating the vertex. Okay, should not. Okay, so and if you are repeating a vertex, that means it's not a path, it's a walk. Okay, it's just a simple definition you should be knowing, but yeah, path you should be knowing. Walk, it's not that important, but the only thing that you should be it's like a red flag is that the vertex should not repeating. So if you have some sort of a graph like this, okay, so if you just think of as D to A to B and B to C, if you are reaching from D to C, okay, so that is one of the paths. Okay, that means D to A and then A to B and B to C is one of the paths. Okay. The only red flag that I told you should not be repeating there can be a very complex graph, right? And then there can be some paths where the same, you are just repeating the vertices, correct? You are just using the vertices twice. Okay, that you should not be doing. That if that is a path, that is not like if you have been given a sort of a long chain edges where you are just repeating some of the vertices, that basically is not a path, that's a walk. Okay, that's just the basic definition. I hope it's not that important also.
Sir, in a path, first node or the first vertex and the last vertex can be same.
Yeah, that can be same.
So how can we consider whether a node or any path through which we are following is a red flag or not?
Red flag. No, I'm just like red flag. I just told you that whenever you are, then whenever you have been given some sort of a edges, right? If you have been asked whether it's a path or not, you should not be in between. If you have, let's for example, you have to reach from some one vertex to the other, U vertex to V vertex. Okay, and if you are just reaching from V to U, you should in between whatever the vertex that is coming. Let's for example, in between a vertex A is coming, so you should not be using A twice. Okay, so let's for example, you're reaching from some vertex U to V. Okay, there is some big graph in between. Okay, so but in between there is a edge, there is a vertex A. So if you are going from U, if you have to reach from U to V, you should not be doing something like that. You're using go and then again you're going back and then coming here. This should not be happening. So if the path, you should be defining like U to A and then directly from U to V, or U to A to B and then B to V. You should not be using A twice. This is what I'm trying to say. If you're using that A twice,
or should not be there.
Repetition should not occur. If you are repeating it, that's a walk. But it's a very basic thing. It's like
yes, sir.
Yeah. Just the definition. The next thing is after path, we'll talk about the graph. Reachability is like for any graph. see, I'll just give you the definition. We'll talk about the reachability again whenever we'll talk the topological sorting or BFS. Okay. So basically, reachability is something for a given plot or whatever the graph that has been given to you. You can be asked whether I can reach from one vertex to the other. If you are able to reach it from A to B, okay, in a bigger graph, whatever the graph that has been given to you, then you can say that you are able to reach it from some vertex A to B. Okay, otherwise not. Is the reachability is simple, like the word itself defines you what do you mean by reachability. Okay, the next part is the graph coloring. Okay, so these are very basic things, that's why I'm going very fast here. So the important portion that wherever it will come, we'll just try to solve some of the problems also. Okay.
Sir, what is reachability, sir?
Okay, I'll just tell you. Basically, see, if you have been given a plot, something like that. So if you have been asked whether can you reach to D via A, is D reachable via A? What will
No.
you say? Like, yeah, yeah, that is what reachability means. Like, can you reach, like, go from A to B? So you can't go it. So no. If you're able to go, then you can say. So that's basically is reachability. Okay. Yeah. So if this is the plot, you can say that yeah, you can reach it from A to B. And one of the path, can somebody tell me the path? One of the path.
A to B
A
to
A to B, E to
Yeah.
C,
A to B, B to C.
A, B, C, E.
Correct. And there can be other
Yeah.
path also. A to B and then
A
E
to
to
E to C, C to
Correct.
D.
A to D. Yeah.
Yeah. Correct. So this is what you mean by reachability and then coloring. Sorry, the path. Okay, I guess this is clear. Yeah, in graph coloring, what happens many times? What happens? You have been given some sort of a map, or there are a number of applications for the graph coloring, like scheduling, some sort of a classing. Yeah. So yeah, it is basically, it can be defined something like that. If you are not able to understand, that is also fine. I'll just can you please mute yourself?
Yeah, express with me. In the fashion little.
Can you please mute yourself?
Sir, I think
See,
you can mute everyone else. It's
Yeah,
better.
yeah, sir.
but they can unmute themselves again, right? Okay. So graph coloring, if you just, it's very, it's a concept such that you have been given some sort of a plot or maybe a graph also you have been given, and then you have been mostly graph coloring basically is like can be used for scheduling some sort of a class says, or maybe you have been given some sort of a map and then can be asked what can be the minimum number of color that you should be using, a different color that you should be using, that uh, that the different number of coloring that you should be using, such that the adjacent vertex should not be having the same color. Okay, so this is the function, like it's the graph coloring is simply a function. C, you can just think of as a C as a function such that you are coloring the vertex. Okay, V vertex that you have, the whole vertex V is a set of vertices that you have in the graph G. Okay, such that UV is all the edges, UV is the combination of edges that you have, okay, in your graph. So graph is when, so you have some sort of a graph G, where G is a whole set of vertices and E is the whole set of edges that you have in that graph. So you are doing a coloring in your whatever the graph that has been given to you, and whenever you are coloring, so you are coloring in such a way that whenever the color for U and V should not be same. That means if you have a plot something like that, and I have to color it. I'll just take some graph has been given here, and it's a bidirectional graph. Okay. So this becomes to be okay. So this is a graph that has been given to you. So all the you can just think of how many vertices are there, 10 vertices, and all the sides you can just think of it. And the edges, whatever the number of edges that you can see here, all the edges. Okay, and now you have been asked, you have to you have to just basically color this whole graph in such a way that you'll have to use a minimum number of colors to basically you have to use a minimum number of color to color this graph, color the edges of color the vertices of the graph in such a way that the adjacent vertex, right? So if can you please mute yourself? So if you are coloring, let's for example this vertex 1 and 2. So here it has been given whenever you have adjacent vertices 1 and 2, the color for 1 and the color for 2
Sir,
should
can you
not be
please
same.
ask the host to mute everyone?
Okay. So I'll just finish this graph coloring and then I'll just you can just okay, you can unmute yourself and then can ask it out. Just give me one confirmation in the chat box. You are able to see my screen, right? Okay, no. Okay. Okay, now I guess it is. So what I was saying about the graph coloring is it's basically a simple graph coloring. Basically, just have to color all the vertices of the graph in such a way that no two adjacent matrix or no two adjacent vertices should be having the same color. In mathematics, you just define it as it is a function C. Just define the graph coloring as C. In such a way, you are coloring the vertex. Okay, you are coloring the vertex with some color in such a way that whenever you have a UV as an edge in your graph, okay, so the color for U and the color for V should not be same. Okay, I guess we're able to understand that. So graph coloring basically coloring of your whole vertices of the graph in such a way that whenever you have a two adjacent vertices, the color should not be same for both the cases. Okay, and in this you have a concept like minimum graph coloring, like minimum number of color that it should be using for any given graph also. Okay, for example for this graph, I'll just give you an example for this. If you have been given this sort of a graph, okay, and then you have been asked how will you color this graph, okay, basically then just think of I'll just start coloring. Let's for example I'm starting, and you should be thinking that if you're coloring this the first stage with the red color, okay, so you can't color 2 and 5 with the red color, right? Because basically that's the graph in the graph coloring. You can't color the adjacent vertex with the same color. Now you can color the second and the 5 with the same color, basically because 2 and 5 are not adjacent to each other, so they can have a same color. They can have a different color also, but I'm just putting the green color here. Okay, even 6 can have a green color because 6, 5 and 2 all are not adjacent to each other. Okay, so even 6 can also have a green color, but okay, that's fine. I'm just not putting the same color here. Okay, or maybe I'll just put it here. Fine. Now you can just think of 2 here. 2 is I've just colored with a green color, and then 1 is red. So I'll just put the blue one or yellow one here. Even I can put here red also, because 1 and 3 are not as adjacent to each other. See, there's a concept. See, I'm just doing the graph coloring. I can use n different color here also, but to make it to optimize that, there's a concept like minimum graph coloring. Like in those cases, first we are trying to solve. We are just taking a different colors. I'm just telling you that the both adjacent vertices should not be having the same color. Then we'll solve this same problem for a optimized one. Optimized one means where you'll be using the minimum number of colors to color this graph. Okay, so first the method that we are doing it now, this just to color this graph. Okay, now the next thing that we'll be doing is to optimize the color, optimize the number of color that we'll be using. Okay, so here also you can have yellow, because 7 and 3 are not attached to each other. Even here also you can have a yellow color. You can just put red here again. You can put even red here also again. And here you can put, you can't put green here, but you can put, even you can't put yellow here, because yellow will be adjacent to each other. So what you can do is you can just put some different color here. So here we have used how many colors? 1, 2, 3, 4. 4 colors we have used it. Now we'll optimize this. Okay, how will you optimize this? Okay, I'll just mute if you have. Do you have any doubt till now in this? Maybe I'll just unmute this.
So what about 7 and 8?
Yes, sir.
Yeah.
Same color on adjacent side, like 7
No,
and
no, 8 and 9.
Yeah. Yeah, this can't happen. This can't happen. Correct.
Oh, sorry,
So
sir,
you
8
can't.
and 9.
Yeah. Yeah, 8 and 9. You can't have the same color. 8 and 9 can't have the same color.
Sir,
7
7
and 10.
sir, 7 and
7 and
10.
10 also, sir.
7
Which
and
one?
10 also, sir. 7 and
7
10.
and
7
10.
and 10.
Even 7 and 10 can't have the same color. Okay.
265, sir.
Yeah. So I can put red here, right? I can put red here. Correct?
Yes, sir. Red is red.
Yeah,
Red or orange.
at 10.
So this was 10. Okay. What next? Okay. But which color can I? Yeah, here we can put yellow, right? Yellow.
Yes, sir.
Yeah.
Yellow or
Green
green.
or
Sir.
Yeah.
green.
Yellow.
as well.
No, green we can't.
Yellow.
Yellow
Yellow.
we can.
Even,
Okay. Yeah,
green we
green.
can't put because 6 is connected
6 is
directly to.
connected. Yes,
Yeah.
sir.
Yellow.
So I guess
Sir,
Yeah.
at 4 we can use red.
at 4 we
Yes,
can
sir.
use red. Yeah, we can use red here there also. Yeah.
Yes,
So
then our color will be less.
so
Then we are
see,
using
what I was
3
saying
colors.
is, that's fine. Everyone has got it. So now, how many colors we have used now?
4 over here, sir.
4 color we have used. And now we have
4
to
color.
optimize this. Okay. Now the same plot we have to optimize it. Okay. So let's optimize the same thing. So now we'll try to optimize this. So now the optimization means we have to use the minimum number of colors, such that we are using the concept of the graph coloring. That means you should not be coloring the adjacent with the same color. Let's do it. So if I'm starting with the first again, So our first node, like basically we are just starting with the first vertices again. So second, 6 and 5 is fine, right? Can we put third with the red again?
Yes, sir.
Yes, correct. So we are just trying to optimize this. So third we can put with the red again. Okay, but yeah. So this is again red. So if we are putting third with red,
But now 3 and 8 are connected.
Not because 8 is red.
Yes, 8 is again red.
That's fine. No, from the starting we're just dealing. We are starting with first.
We have to put yellow.
2, 6, 5 is fine. Green is fine. Then we are just putting 3, and we can So 3 with red, that is fine. 3 and the connection with even 4
is connected to it.
Right. For 4 we have to. Okay.
I'll just draw it out so that.
How can 8 and 3 is of the same color red?
Yeah. We are doing it. We are correcting that.
Going with the flow.
Then you have 6 here. You have 7 here. You have 8 here. You have 9 here, and you have 10 here. And how is the connection? 1, 3. Then we have connection directly here. Okay. 6 is connected to 8. 6, 8, and 9 is connected
to 1, 8, and 9.
2, 7, and this is connected, right?
So 6 is connected to 1 also.
Okay, 6
1
is
and
connected
6.
to
1 to 6.
Earlier we were having a different color here.
Are also connected.
3 and 8, sir. 3 and 8.
3 and 8 are also connected.
Okay, 9 and 4 are also connected. Any other thing that we are missing? No.
No,
No, sir. It's okay.
Let's optimize this. So earlier we were using 4 color. Now let's take red here. Green, 2 is green. Even we can put 6 also as green. 5 also as green. Correct?
Yes, sir.
Yes, sir.
Okay. Now again we can put 2 as red. Even 3 we can put it as red.
Yes, sir.
Correct?
Yes, sir.
Now to color 10 we have to use a different color, right? Because we can't use red, and so we have to use.
Sir, 9, sir. Sir,
We can
9.
use red for 9.
Red for
Red
9.
we can use it for 9. That is fine. So for 10
And yellow
we'll
for
have to
8
use a
and
different color. We'll have to
Yes,
use
sir.
10 different color for 10 because we have a connected node with red and green, so we can't use the same color. Okay, so for 3, 8 we can't use. Again we have to use some different color for 8 also, because we can't
we
use.
can use
For 8,
yellow.
Yellow can be used.
Yellow, sir.
Yeah.
Yellow, sir.
Yellow, correct.
For
Yellow
4,
we can
yes.
use it.
4 also yellow.
9 red.
Yeah. 9 for
4,
red.
correct. On 9 we can use red
Red,
again.
sir.
We can
Red.
use it. Yeah.
Red.
So now how many of we have used? 3 colors.
3.
3 color.
Only 3.
Correct. So we have optimized
Yes.
it. So in the exam, you'll be asked this type of a problem, like what can be the minimum
There are
number
4
of
colors, right?
3 only, right? Red, green, and yellow, right? This is the optimized one. This is a normal case. That can be a one case. Somebody can color it like this also, because here also whatever we were trying to do is followed here. Like the adjacent vertices should not be having the same color. Correct? But this is our optimized, like where we are using the minimum number of colors to plot to color our vertices, right? So this is our optimized version. Okay.
But for coloring,
Okay,
do we
sir.
have to follow any kind of basic criteria for that? What is it?
No, there is
Because we
steps. You don't. I don't think so. There is any steps that you should be following. You can start with. We can just start with the vertices which have the maximum number of connections, or you can say the degree. Okay, degree I haven't defined, right? So I'll just define the degree. Or you can just think of as a from where, for whichever the matrices, for whichever the vertices, there is a large number of what you can say, the connection is there. You can start with that, because if you're starting with that, you'll be having, you can put maximum number of edges, right? So we have started with, let's for example here, one was having 3 as compared to, even 2 was having also 3, 5 also. But if you are starting with some vertices where the connection is largest, what you can do is you can just put one wherever you are starting as a one color, but you'll be having like if one vertices have a 5 connection, you can just put the whole 5 things as the same one color, right? Correct, if there is a no other connection. Okay, let's again, I'm just putting one example. You can try to solve it out. So okay, now you have to tell me the optimized version of graph, like basically the minimum number of colors that it will be using to color the whole, minimum number of color required to color the whole vertices of the graph.
For the case, B, D, E, C can be in the same color.
Okay, let's start with
B, D, E, and C, which can be of the same color.
okay, so where should I start? Should I start with A or the other one?
Yes, sir.
Whatever.
Yes, sir.
Yes,
Okay, start with
anywhere, anywhere.
Okay, put A as red.
So
Then
if you
B
need
and C.
B,
should
C,
we
and H, a common
H?
color.
B I can
F.
put as same color. B and C will be having a same color, correct?
And H
Yes,
also,
Okay,
sir.
yes, sir.
Even H also I can put it as same color, because you
Yes,
can see that,
Hello, sir.
right?
Yes, sir.
So why V, H, and C as the same color?
See, because
Not adjoining side.
see in graph
Because
5
they are not
we are,
sharing any edge.
yeah, we are not, yeah, that's why, because that is not sharing any edge, so we can put some different color apart from the red one. If you are putting red here, so that's the main condition, right? We have defined graph coloring as what? It's a function C such that we are coloring the vertex V, the whole vertex V, in such a way that whenever you have a U V as an edge, the color of U and the color of V, the vertex V and the color, this should not be same, right? This is what we have defined as graph coloring, correct? So the color for U and V, whenever U, V are edge, UV is a edge means what? U and V are adjacent to each other, right? The vertices, if U and V making a edge, that means U and V are some adjacent to each other, the vertices. So the color for U and V should not be same. That is what we have defined as a function for graph coloring. And in that graph coloring itself, we are optimizing that graph coloring. That means we are finding the minimum number of color that should be required to color a whole, like the graph that has been given to you. Okay, so that's why we can't color A, B, H, and C with the same, like the red one. We can color B, H, C with the different colors. Okay, that you can do it, but that will not be your optimized version, because we are trying to find out the minimum number of colors. So that's why we are trying to put it the same color as B, H, and C. Okay, whatever is connected to A. Now the next thing what you can do is, if we can have to put what
No, sir, we can
F
use
with
red color
red
for
color,
effect B.
yeah, we
red
can
color,
use,
sir.
F
F
and G as a red color.
yeah, red we
Okay.
can use it again
D
for,
and G.
D and F.
we can,
No, D
D
and
we
G.
can
D
use,
and G, sir. D and G, sir.
D and
D
G.
and G.
E and F yellow, sir. E and F yellow and G red.
okay, so D we can, or even this we can read, we can
Yes.
use red,
Sir,
right?
yes,
Yes,
sir.
sir.
Yes, sir.
Yeah.
Many
And
we
E and F yellow.
And
F
then we can
and
use
E.
any other color,
Another.
Yeah,
Yes, sir.
correct? So we are
Yes,
using
sir.
how
Yes.
many? The
Three
minimum
colors.
number is what? Three
Three
colors. So
colors.
I guess
Regular.
if you'll be asked in the exam, you'll be able to solve it, right?
Right.
Yes, sir.
There
Yes,
must
sir.
be, yeah. So there must be one
Yes.
question. First, like every time you can just see that every time that there are one questions that will be asked regarding the graph coloring. I hope you'll be able to do that. Let's move to the next part now.
Yeah.
Okay.
Hello, sir.
Yeah.
Sir, in the lecture, sir mentioned about a term called four-colored theorem.
Can you please explain something about this?
It has been defined something like that, like any map that has been given to you, you should be using the, like, that's a theorem that he has, like, not, it's like a very difficult to prove. That is what he told. Even I'm not much aware of that theorem. He just told that there is four color theorem, that any map that has been given to you, you can just use maximum 4 number and you can do that. You can do the graph coloring. Basically, you'll be using maximum of 4 color that will be used to do the
Means
graph coloring of any difficult. Yeah,
any connected graph can be colored using 4 colors only, not more than that.
this is what has been defined. Yeah.
Okay, sir. Okay. Thank you, sir.
Right. So the next thing is the adjacency matrix. That is very simple. So adjacency matrix, see, if you'll just define it, maybe you would have read in the CT computational thinking also, right, about the adjacency matrix. So for any matrix that has been given, so I'm just defining first for the undirected, and then we'll deal with the directed one also. So 3,
Okay, sir.
4, 1, 2. Okay, if you have to just write it in the form of a matrix. Okay, so basically you have a 4 vertices, so we'll be making a 4 cross 4 matrix. Okay, and in that matrix you'll be putting the values. And how will you put the values? So this is how you define adjacency matrix. For A, comma I, J equals to 1 if there is a connection, if A and J, I, J belongs to V. So I, basically I and J are the some vertices, I vertex and J vertex. So in the matrix you'll be putting 1 if there is a I and J is sharing some sort of a edge. Okay, and that will be 0 if I and J doesn't belongs to the edge, or there is no edge between I and J. If there is an edge between I and J, you'll be putting 1. This is for defined for undirected. Okay, now you can say the bidirectional. So if you have to write the adjacency matrix, how will you write? So let's start with this. You'll be having this. You can just write it here: 1, 2, 3, 4. 1, 2, 3, 4. So is there any connection from 1 to 1?
No,
So
sir.
we are not dealing with that self loop. Yeah, self
No,
loop we
sir.
are not reading, so there is
We'll
no
put
connection.
0 there.
Is there anything from 1 to 2?
Yes, sir.
1. Yeah, so we'll be putting 1 here. 1 to 3, there is, yeah.
1,
Yeah.
1 to
1
4,
to
there is
4,
nothing.
0. No, sir. 0.
0.
2 to 1,
2
yes, sir.
to 1. 2 to 1
Yes.
is yes,
Yeah.
Yes,
because
sir.
if it was
It's
given something like
bidirectional.
that, then you would have said that
Then
2
it
to
will
1 is
be
not
It's
possible.
bidirectional.
Yeah, because it's a bidirectional. So for 2 to 1 also, you'll be writing it as a 1. So I'll
1.
just write it as 2 to 0. So for 3, 3 also it will be 0. For 4, 4 it will be 0. And it will be a symmetric matrix. Okay.
Yes,
So
sir.
I'll tell you why it is symmetric. Because 2 to 3 is any connection, no connection. And okay. And then you
Yeah.
can just one here, write it here.
1 and 4. 4.
Okay. This you can see that this is a symmetric matrix, right? Symmetric matrix, you
Yes, sir.
understand
Yeah.
what? So if you're just taking this, it will be symmetric about, if you just think of this as a mirror, it will be symmetric about that.
Diagonal.
Yeah, diagonal. Yeah. For any undirected graph, whenever you have been asked about the adjacency matrix in the exam also for undirected graph, and in any of the option that graph, that adjacency matrix that has been given is not symmetric, you can just remove that option. Okay. So that must be,
Yes, sir.
that's a very important, yeah, that must be a symmetric. That's one of the properties also for undirected graph. And many a times we'll use the basic concept of the symmetric matrices also. So this is defined. Now let's deal with some of the, like if you have been given the directed graph. Okay. So the same example, if you have been given something like that, one. Okay. So this is, see, basically this is from I through to J. Okay, you can't just think of as a J to I. This is basically I to J. Okay. If you have been
Yes.
given A I to J means equals to 1, that means A I to J means there is an edge from I to J. Okay, you can reach out to J from I. Okay, It's not the other way. So for this plot, if I have to write the adjacency matrix, how will I write? Can you tell me how will you write?
Yeah, it is
0, sir.
1 to 3, 1 to 3 K so 1 here.
1 2. Okay, so this is how it has been. 1
1
2
to 2
you
1,
can
sir.
reach out.
Yes, 1.
1
1 to 3 1.
1 and 3 and 1.
1 2 4 0.
0.
2 2
2
2
2
2
1
1.
it's 0, sir.
It will be 0. So did you got
2
the
to
idea,
2
right? 2
2
to
0.
1 you can't reach.
Yes, sir.
1 to 2 you
2
can
2 to
reach
2
out,
0.
but 2
2
to
to
1 you
3
can't reach.
0. 2 to 4
2
0,
we
sir.
cannot
All
reach
0.
anywhere.
Yeah,
Yeah.
from 2
Nowhere.
you can't. Yeah, from 2 you can't reach out to anywhere else, because you can
T
see that both of the edges, it's like inward edges, right? So okay,
Yes.
I'll define the degree also now. So from 3 you can reach out to 4,
to
but
only 4, sir.
Only
Only 4
4.
1.
3 to
Only 4.
Only 4. Yeah.
from 4 you
4
can
to
reach
only
out to
2.
2.
1
4
only
to
2.
1.
Okay, so this is how you write the adjacency matrix for, and you can see that this is not symmetric. Like you can get a symmetric
Yes, sir.
matrix sometimes, but it's not always
Yes.
symmetric. But for undirected, it will always be a symmetric plot. Okay.
Symmetric.
Yes.
Hmm.
Okay,
Sir,
okay.
I have one question.
Yeah.
Sir, over in this matrix that we have shown, can you just scroll down a bit? So,
Yeah.
sir, in this area, so we are just watching the direction of the directions, and then we are putting them as 0 or 1. For example, as I'm over this graph able to go from 1 to 2, so I'm putting it as 1. So if the question
Correct.
comes, if I want to come from 2 to 1, then it would be 0.
Correct, because you can't go from 2 to 1. There's only, you can just think of as a 1 and 2 in some places. Okay, there's a flight from 1 to 2, but that flight doesn't come to 1. Okay, so you can't come from 2, you can't go anywhere. Like basically there is no, you can't go from this place to anywhere. There's no flight from there. Okay, you can
And
just think
sir,
of in that way.
another question is that if there is an arrow that goes from 2 to 1, then will it be considered as a matrix, or
Yeah.
it would be null and void?
No, if this is been given like this, 2 to 1 also, then you will just write it here 2 to 1. Where is that? 2 to 1 also as 1. Here you will be writing it as 1. That's it.
Okay, sir. Thank you.
Sir,
Got it,
for
right.
2
Okay.
to 1, we consider column to row.
Column to row. If you are just thinking, see, this is how, okay, these are all columns, right?
Sir, rows, sir.
Row, sir.
So those are rows.
Yes, sir, those are rows.
Horizontally, you write it column, rows, right?
Rows, horizontally.
Yes, sir, rows.
Vertically, it will column.
Vertically, you write it column. Okay, so these are the first, second, third, fourth rows, right?
Sir, for directed, we have written Aij is equal to 1. So for undirected, how will we write the same equation?
No, you'll be writing the same thing, Aij, but you should be thinking that the definition that I have defined is for both undirected and directed both. The only thing that you should be considering is for undirected, for you consider Ji also as a edge, right? Because Ij, if Ij is a edge, Ji is also a edge, right? For undirected.
Yes, sir.
Yeah, but that's not true for directed graph.
Okay, sir.
Okay, is this clear to everyone?
Yes.
Yes, sir.
Yes, it's clear.
So let's move to the next thing. Now the next thing, okay, so I haven't defined the degree for any graph that has been
In degree
given
and
to
out
me.
degree.
Yeah. So basically for a directed, basically that is defined the degree for a directed graph. You define two things, right? In degree and out degree. Okay, so in degree is basically the number of edges, okay, that is coming towards, okay, so this is basically towards that particular vertex, and this is what, this is away from vertex. Okay. Okay. Let's write an example. If you have been given a plot, something like that.
So it's just like a airport jet.
What?
It's just like an airport that some plane comes and some planes go.
Yeah.
You can just think of in that way. Yeah. Okay. So for what can you say about the in degree of B? Just let's write in degree and out degree.
There is no in degree of B.
2 in degrees on B.
Two.
Oh,
Two
sorry,
degree is two, sir.
two. Out degree
2
is
in
zero.
degree, right?
Out degree
Out
0.
degree is 0.
Out degree
correct?
is zero.
Out
Yes,
degree is
yes.
0.
What about this?
In degree is 0, out degree.
Two out
Only
degree, sir.
2 out degree.
Correct. Similarly for this,
Yeah. Two out degree.
3 out
2
degree,
out
1 in
degrees
degree.
and
Two
3
out
out degree.
Three out degree,
Two out
one
degree and
in
one degree.
correct? I guess
Three
you
out
have
degree.
are
Yeah,
able to
it's correct.
understand this.
Yeah, it's correct.
two in.
Okay. So one more thing, one important concept for a directed graph, there is nothing called degree. Okay, you should be knowing that in degree or out degree. The degree is
Yes.
defined for an undirected graph. Okay.
Yes.
So if the same plot, if there was no connection, it was something like 1. Okay, whatever it is. Okay. Now, if it is a bidirectional graph, then if you have been asked about the degree, so we can say that directly the degree is 2. There is nothing. This is because this is an undirected graph. But you can't say that for a directed graph what's the degree. You should be knowing in degree or out degree. And the total number, and one more thing, you should not be doing something like the total number of degrees in degree plus out degree. Okay, no,
Yeah.
that is not correct. Okay, that is not correct. The total is not equals to the in degree plus out degree for a
In
directed graph.
computational thinking, sir, total degree in degree plus out degree.
Okay, but here you don't have to follow that. Okay, for a directed plot.
Okay.
For undirected, you can directly say that whatever the number of edges that are connecting to that particular vertex, that is the number of degree for an undirected plot.
So,
or
sir,
a
how it
undirected
is
graph.
2 right now, sir? And on 3 points, there are 4 paths are there. So, the degree should be more, right?
Where? Here, the degree is 4, right?
Yes.
Yeah, the degree is 4. For this case, the degree is 2. For this case, the degree is again 4. For this case, the degree is 2.
But there is no concept of in degree and out degree for this graph.
There is no concept of in degree and out degree for an undirected graph. For a bidirectional graph, there is nothing called in degree and out degree. And there is nothing called degree for a directed graph. Okay? Only the in degree and out degree.
Okay,
Clear?
sir. Okay, sir.
Yes.
Okay. Let's start with a new concept, that is the independent set. Here also, independence, like the way we have defined for the graph coloring, okay, there is a concept independent set also, and there also we maximize the independent set. Okay, there is some optimum thing also for the independent set also. So in the graph coloring, the optimized value was the minimum value that should be required to color a graph. Here, the maximum value that will calculate. So first I'll define for an independent set. So then you have been given a graph G. Graph G has been given with vertex V and edges E. Okay, so this is a set of all the vertices V, and E is the set of all the edges. So the next thing that is for independent set is basically this is independent set is what it has been defined as this is a subset of V only. So V was of our vertex. So this V is a collection of all the vertices, right? So you have a smaller chunk V, vertex V, such that no two vertices are connected by edge. See, I'll just explain it again. So you have a vertex, you have a subset of V. So V is a collection of all the vertices. And now in this, you have defined a new set that is, let's for example, A you have defined. This A you have defined as an independent set. So A will consist of some vertices. Okay, so A will be consisting of some of the vertices from V itself, because that A is a subset of V. Okay, such that no two vertices are connected by the edge. Let's for example, this has been given as a graph itself. A and B are the vertices only. For this graph, this simple graph, A and B are the only vertices. If I'm writing A and B both, will this be an independent set or not? Just read the definition again and tell me. No. And if I'm writing A directly, A only, now is this an independent set?
Yes.
Yes.
Yes, sir.
Yeah, this is an independent set, because what did I say? It's a subset of V. So V basically is what? V basically is is a all collection of vertices. But A is what? A star, you can just think of. A star is what? Is an independent set, such that that's a subset of V, but there is a one more condition. The first condition is that should be a subset of, like, the vertices should be from the vertex B. But the other condition that it should satisfy is no two vertices. So whatever the vertices that are there in A star should not be connecting to a edge. Okay. So if you are writing A, B, that means it has been an edge, right? That should not occur. If you are just writing A, that is fine, because that is not making any edge. Is it clear to everyone?
If we write B, then
Yes, sir. Yes, sir.
Even if we write B also, that is also fine. It's also independent set. So independent set can be, it's not unique for a graph. You can have a like different types of independent set. Okay, you can get the different types of independent set. What?
In above graph in A and B, there are no edge between them.
Yeah, just taking A only, that means what? A is a subset of V, right? Because V consists of A, B both. But only A doesn't make any, because you don't have anything else, right? So that is not making any, A alone doesn't make any edge, correct? Are you getting me?
Yes.
Okay, let's a bigger example that will help you. So let's, for example, you have some sort of exam. Okay, now we have to get the independent set, and then we have to optimize that also. So if I'll start with somewhere, let's start with one vertex, V1. Let's start with the vertex 1 itself. If I'm starting with vertex 1, let's cut it out. What should I write here? The next
8, 6.
6, sir. 6, 8.
No, 2 is connected, right? So 2, first of all, we'll write 2, correct? Because 2 is connected to that. If A is not included, 2 can be included, correct?
Okay, sir.
Yes, sir.
Yes. Sir, it's better if you write 1 and cut the vertices that are connected to 1. In that case, it will be more clear. Yes, sir.
Okay, that also we can do, correct? Okay, then let's do it by that way. So I'm just taking A into consideration. So I'm just cutting it out. 2 is cut down because 2 you can't use.
4 will be also crossed, and 5 will also get crossed.
Yeah, 4 you also can't use, correct?
Yes.
5 also you can't use. So 5 also you can put it here. What else?
7, sir.
I didn't say it like this, sir. So you could just 2 and 5, instead of 2 and 5, you just write down the 1, sir. and then this 4, 5, and 2 will get crossed.
Okay, that also we can write it. But the
Yes,
first thing is we are just taking into consideration of we're starting with 1. Then if you're excluding 2, 5, because 2, 5 doesn't make any 2, 5 doesn't make any edge, right? So 2, 5, 2.
Sir, 4 also.
4 will also
4
come
you
there.
can 4 you can include it.
It's 7.
If you have just taken 4, you have taken, right? That means you can't take 3. So 3 will get cut out. You can't
Sir,
take 8
7.
also. Yeah, 7 will be included. Correct?
Yes, sir.
Is this clear? So 2, 5, 4, 7. So 2, 5, 4, 7 is not making any edge, right? You
Yes.
can just see any of the combination doesn't make any edges. Correct?
Yes.
Yes.
Can you explain this again?
Okay.
Sir,
So
now
this
explain in
example.
my way, sir. The method I explained first. It will be more clear in that way.
Okay. You can just tell me your method.
No, it's not my method. Actually, in the lecture also, sir explained that way only.
Okay.
What sir did was he first take this one vertices 1, and then he cancelled these vertices that were connected to 1, and similarly the vertices that were, and then he took another vertices, and then he crossed the vertices that were connected to that 8, and like this he made the first set, and then
Correct.
all the
That,
crossed, yes, all the crossed one he put in another set, and he said that it is another one independent set.
yeah, that also you can do. You can just think of in that way also. Let's, for example, what you are saying is, let's take V2, the vertex 2. If you are just taking vertex 2, correct? That means you are just cutting down 1, and 3 you are cut down. Correct?
6
Even
also.
you can cut down 6 also, you can cut down. Correct? Because you have
Yes.
taken 2, so you can't take 3, you can't take 6, you can't take 1. Right? Now you can take what? You can take, let's for example, you are taking next
7.
term is 5 or
Yes.
7, whatever it is. 5 if you are
Yes.
taking, 5 if you are taking, then you can't take 8. 8 is cut down, right? 8 is cut down. Now the next thing is
6 is cut down.
6 is already cut down. So 6 is
Yeah.
already done.
May
6 is
4
already
and
6 we,
7.
And now
now
remaining
we are
7
left
and
with
4.
4 if you are taking, the connected one is 3 is already done, 1 is already done. The remaining is what? 7.
7, sir.
Yes. This yes.
Yeah.
And
So
the
you can start.
and the
So you
remaining
can,
cut one will form another independent set.
that also will form another set. You can start with any of the vertices. Okay, we have started with 2. You can start with 1, and then you can just cut down 2, 4, 5, something like that. Okay, so I guess this is how you can start with also. You can do it. It's clear.
Yes, sir.
Clear, sir. Clear.
So it's just that you have to make a subset of vertices V. You have to make a set V. Okay, so this is a set V, something like set S. You have to make a set S such that no two vertices. So whenever you are taking any combination, that should not be connected by the edge. Whenever you see the original graph, okay, so there should not be any connection from 2 to 5 or 2 to 4 or 2 to 7. That should not be there. Okay, and that set you have to find out. So that basically is an independent set, correct? And now you have to optimize that. What can be the maximum number of set that you can get it from the original graph? Okay, this you have to do. How will you do that? Like randomly, you will just do the independent set you have to take out, and then out of that one will be the maximum. Like that will be having a maximum number of sets, maximum number of vertices. Okay, that will be your optimized version.
Is there
Yeah,
a
there is a method.
Is there
Yeah,
a
you can do.
systematic way?
Yeah, there can be one method that you can do it. Okay.
What is that method?
Sir, I have
Okay.
one question in this graph only. Can you just show?
Okay. Yeah. Tell me.
Sir, there are connections between 1, 2, 3, and 4. So if, for example, let me say that there is no connection in between this 1, 3, and 4, so then how it would be? How will we do this thing?
Okay, there is no connection between what?
1, 2, 3, and 4. The outer connection that you have made. If there was no connection, then how it would be made? Yes, sir.
Okay, if there's no connection. Okay, let's start writing it now. If you'll write it, let's start thinking from the. Again, you are taking 2. If you are taking 2, So you just took out 2. So now
only
you
6
can't take 6.
down.
You can't take 6. What?
Except
The
6,
6
all
goes down.
vertices will be included, sir.
Yeah, you
in the
can't
set.
take 6. Now you'll have to go
Hmm.
through. Let's, for example, you're taking 5 now. So if you're taking 5 now, that means you can just cut down 8 and 1. You can't take 8 and 1
Yes.
because if you're taking, that will be making a is, correct? Now the next thing that you should be taking is, you'll have to take 7. If you're taking 7,
We can't
that
take
means you'll cut down
3.
3. Correct?
Right.
Now you're left with 4. So 4 you can take. This can be your independent set.
Sir,
Similar,
is there
sir.
any way of taking them? Is first you have taken 2, then 5, then 8, and
Anything
then
you can take. Anything you can take, and then go ahead.
so
Any
there is
vertices you
no
can.
order of taking.
No,
Right.
no. So that's why I'm saying that, and you can have a n number of independent sets. Like you can have a different independent sets. Like each of us can have. If I'm starting with 1, because 1 I was not taking. If I'm taking 1, let's for example, that means what, I will cut down 5. Correct. So I'll take the different, the 6th one. I will take it again. So 2 I'll not be taking. Correct. Similarly, if 6 is included here, you can't take 7. Okay, you'll have to take 3. So basically, you can just do the complement of this.
Okay, sir. Okay, sir. Thank
Got
you.
it.
So there will be number of sets of independent sets.
So there can be n number, but so the important thing is what you have to calculate the optimized version. That means you have to take out of this whole sets that you are getting, subsets of V. You have to take out one of the version of subset of V, where you have a maximum number of the cardinality of that set should be maximum. Are you getting me? The number of elements that is present in that subset should be maximum. Okay, that's the optimized version. So we have done the optimized version for the graph coloring. Now we have to do the optimized version for the maximum independent set. Okay, so basically for all the independent set that you are made, you have to calculate the optimized version. The one method is minimum. Okay, I'll deal the optimized version after doing one concept, that is the minimum vertex cover. That minimum vertex cover, are you aware of that minimum vertex cover? What is that minimum vertex cover?
No, sir.
Using a few edges, we are able to cover the entire vertex present on.
Correct.
In the
So
graph.
what's the minimum number of vertices that we'll be using for any graph that has? So basically, the minimum graph cover is defined as the minimum number of edges, or not the edges, basically the minimum number of vertices that you'll be using, such that you'll be covering the whole edges of your graph. Okay, I'll write it out. And from here, it will be very simple for us to calculate the maximum independent set also.
So it
That
will
is
be
helpful.
same as the path, or it will be different?
Path.
Is
Can
it
you
the
repeat it?
shortest path to reach from a particular point to the another point?
Yeah, maybe the shortest path.
That is a different concept. I'll go
Like
through
suppose I
that
have
also.
to reach from S1 to S10, so what will be the shortest path to reach
It's
there?
That also will, yeah. That
like
also will
coloring of
define.
the graph.
Yeah. So minimum vertex. So basically, for any vertex cover we were defining. Vertex cover is simple. Like this also again is a subset. So that whatever the vertex is, let's for example, this is a subset S that will also belongs to our original set of vertices V. Okay, if you have a graph V comma E, and V is a collection of all the vertices, E is the edge. So this also the vertex cover, if you have to calculate the vertex cover, that's a simple vertex cover. Then again, we'll be having the minimum vertex cover. So if you just have to take care of the vertex cover, that will also be a subset of vertex V, such that for every edge in the graph, at least one of them must be the part of the vertex cover. For every edge, I'll just write it out. See, so whenever you are making a set, some set that is also a subset of your original vertices, okay, whatever the vertices, the subset that you have taken, whatever the number or the collection of vertices that you have taken, okay, it should be such a way that you are able to cover the whole graph. Okay, are you getting me? Or the whole graph means the whole edges that are present in the graph.
Just like we do the coloring of the edges, like for the vertices.
The coloring was a different concept. Coloring was like
You want to means
that was
cover all the vertices, right? All the vertices.
here. All the you have to take out the collection of vertices such that you are
Okay, sir,
able
okay, sir.
to reach out. You are able to reach out to hold the see. If let's for example, I'm giving one example. A is such a. It has been given B, C, D. Okay. I'm just taking A and B. Is this our vertex? Will this A and B set A will cover all the edges?
No,
Why no?
because we have three edges over here and we have just connected only.
No,
We have
when
just touched one.
Yes, sir.
no. See. Again, what did I say? For every see, if you are taking
Only
the
A will
subset of okay, let me finish it and then you
Okay.
can ask. Okay. So what did I say? That it's S the vertex cover is a set S that we are creating is a subset of V vertex V. Okay, for every edge in the graph, at least one of them must be the part of that vertex cover. Okay, see, if A and B I'm taking, if A I'm taking, that means this edge is covered, this edge is covered, this edge is covered, right? Even if you're just taking A, that itself is covering all the edges of this plot. B we have taken, B can be there. Okay, this can be one of the vertex covered. Okay, and if you have to just write the minimum vertex cover for this plot, you can just write it as A itself. A itself is sufficient to cover all the edges of this graph itself. Is this making sense?
So are we trying to cover
Yes.
edges or are we trying to cover the vertices, sir?
Edges.
We are trying to cover the edges.
So
Every
then
edges
why are
of
we
the graph.
saying vertex cover? Shouldn't we say edge cover?
Because we are making the subset, we are taking out the subset of vertex only, right? So the subset, the S subset that we are making, that itself is a collection of vertices that we are choosing out. See, if you have some sort of where basically we can use it. So basically you can just think of there's a big room and okay, so there's like A room, B room, C room, D room. Where can you put one camera such that you'll be able to cover the whole B room also, C room and D room also. So A is the best place, right? To just put the camera here and then you can just, because from A you already know that you can cover B, C, D. If you're just putting a camera at B, you'll just be able, because there is a connection from B to A only. So you can just cover A only, like this whole boundary or whatever you want to call it. You can't cover this edges and you can't cover this, right? So where this type of application can be used in vertex cover. But here also we are optimizing something. So we have to optimize here. That means you have to find out the minimum number of vertices such that it will be able to cover all the edges. Okay, so for this case, if this was our graph, there is a connection from A to B, A to C, and A to D. Only A, if you're just taking A as a vertices, that was sufficient to cover the whole edges. Correct or not?
Yes.
Yes.
But AB can also be a vertex cover. There's no problem, but the optimized version is A. Okay?
Yes.
Okay. So now we'll mix this minimum vertex cover and the maximum independent set. Okay, so there is a nice relation between these two. Okay, so one is the complement of the other. Okay, if you are able to find the minimum vertex cover, and as compared to the maximum independent set, minimum vertex cover is easy to find, right? You just have to choose out those vertices such that you're able to cover the whole edges. Okay, are you able to understand this topic, or may I repeat? Like
Yes,
you
sir,
want
I'm
me to repeat? Everyone is clear with this? The minimum vertex
Yes,
cover
sir.
and okay. So let's
Sir,
solve one problem. Yeah. Go ahead.
So I'm trying to understand its definition, vertex cover. Can you just tell me whether I'm right or wrong? I say that a vertex cover is a subset of V such that for all edges E1 belonging to set E, there is at least one vertex that belongs to VC.
Correct. That's the correct.
Okay, sir.
Or if in this, or in the layman term, you can just think of like I told you, right? If you're just defining minimum vertex cover, that means you just pick out those vertices such that you're able to cover all the edges of the graph. That's it. Okay.
Oh, sir, can you please repeat? I just missed it.
Okay, so minimum vertex cover is generally defined it as you're just making a subset of V. So the original V was there, so you're just making a small subset of V in such a minimum number. The cardinality should be minimum, okay, for us minimum possible vertex cover. Okay, minimum number of vertex that you are choosing out, such that you are able to cover each and every edges of the graph. Okay, I'll just write it out. So minimum possible subset of V. Let's, for example, you're just V dash is your subset of V. Okay, V dash is your that you are making out the minimum vertex cover, such that it covers all the edges of the graph. Maybe with the example that will be much clearer. Okay, can I go with the example? Let's solve one example. Okay, there's a plot. Yeah. It's like
CCTV.
You can just, the example that I gave you can just think of in that way. The minimum, if you are just building some bigger building, and then you have to use the minimum number of cameras so that you are able to cover each and every corner of your plot. Okay, and that you should be using the minimum number of cameras also. Okay, you have to optimize the number of cameras. Okay, so that this method can be used. So then the connection, you can just put it. Okay, the same connection will put it. B to C there is a connection, A to F there is a connection, and G to F also is a connection, and we'll connect each and everything. Now you'll have to find the minimum vertex cover for this plot. So here you can just start with, see, here can somebody tell me which vertex should you start with? If you have to cover the whole edges, you should be starting with that vertices that has a maximum number of edges, maximum number of degree, right? So that will be covering maximum. Okay. So where is the maximum?
I think B.
Okay, let's connect this also. Connect this also. Now H has the maximum, right? 1, 2, 3, 4, 5. Even all.
Yes, sir.
Okay, let's start with.
H
If
has
I'm
maximum,
include. Okay, so we are making this vertex V dash. We're making V dash. V dash will be the subset of V, and let's say the subset that we are making is the first one is H. If you are taking H out, so which of the edges have been covered? This is done. 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 Which is the next I should be taking? I can take anything else, right? Let's
B or C.
Let's take B. If I'm taking B, what are the all edges covered? This will be done. This edges will be covered. This edge will be covered. This edge will be covered. Correct? Anything else? Yeah. What should be the next one?
F.
If you had
E.
Okay, even if you are taking E,
But
let's
we are
take D.
reaching E from H.
Sir, can't we take C? Because in
You can
C
take
there
C.
is
You can take,
covered.
in spite of B, you would have taken C also. There is no problem. Okay, we'll do with that also. Let's take D. If I'm taking D, what all things that will be covered? This will be covered. This will be done. Correct? What are left now? What do you think? Which one should I take?
The GF is left, sir.
G, if I'm taking, this is done, this is done, this is done. Okay, I have to take C also, correct? To finish this and this.
Yes, sir.
Correct?
Yes.
Okay, so here you can just apply one, you can just start with that vertices that has the maximum number of, you can say the maximum number of degree. Okay, you start with that and then you can go ahead. I guess you can, is this clear? This minimum vertex cover?
Yes.
So basically, in this, we just have to look for the edges, right? Not for the nodes.
Basically, yeah, you have to just look.
If we choose
Cover up all
HCB.
the edges. Yeah.
Yeah, so see, if you have taken H, that means which all places is covered. This edge is whole covered, this is whole covered, this is whole covered, this is whole covered, this is whole covered. What else is left? Okay, whatever left is, whatever the edges which are left, now you have to choose out that vertex that can help you to cover the maximum number of edges. Okay, or go to that vertices which are the highest.
HDE would have taken care, no? HDE, although
H,
DE.
H, let's say H, B,
E.
H, E, you are telling. Okay. Then how come?
DE.
Okay, you're saying D and then E.
D, you can delete the B one. B delete. Don't delete the B.
Okay, Bombay, I can delete it. Okay.
HDE would be, I think, more, it will complete the entire graph.
Okay, it will
FG is
complete.
missing then.
I want to say HBC. It will cover all.
No. D and E will not come together. D and E will never come together.
Right?
It's not, there's no such condition.
G and C, how come it is coming together? G to C connection is there, sir.
There's no such condition that you cannot take adjacent vertices.
No, here you can take anything. You just have to
But
cover
HDE
the
will
whole
cover
edges.
No, HDE won't work. There are many like edges that are not getting covered.
Yeah,
in this.
that are left. I guess I
C to C,
also
C
agree.
to G.
Okay.
For example,
Yes.
the segment FG is left out when you take HDE.
If you are taking only HD, if you are just taking HD, see, this
A
is
is not
covered, this
covered.
is done.
FB and
This is done.
definitely. FB will.
This is done.
No, that ACG
FB and
area won't
CG
get
will
covered.
be left out.
This is done. But here are so many other things like this AB connect edge is left. This even BC is left, right?
And FG
This
is
done.
also left. The
No,
segment
even
FG
this is left. Yeah. So many things are left. Okay. So you'll have to there is no exact method. I can just tell you that if you have been asked to calculate, you can just start with the maximum where there is a maximum number of degree you can start with that vertex where there's a maximum number of degree. Okay, and then the next step what you can do is you can just go ahead and then whatever is left you can just think of and then
Sir, then in this case, then HD is violating the condition, right? B is having degree 4 and D is having only degree 3. No, it is actually 4. Okay.
No, you can just
if
you want me to write it, see, I'll just write it. Pick the vertex with highest degree. The first step can be this one. The second step, what you can think is, now you have to go to that vertices.
But in this graph, sir, I think all the vertices are having same degree, I think. Only A is not having.
We can take adjacent side.
No, A is at H. B has 4, right? 1, 2, 3, 4.
H has maximum.
H has 5, right? 1, 2, 3, 4, 5. Correct?
Yeah, only H is having. Rest all except A. Rest all is having 4 degree only.
So this is what I said, right? Pick the vertex with the highest degree. You can have 2, 3 vertices, but it's fine. Like you should not be like, it's not that you'll be getting a unique answer. You can have different answers, right? But you'll have to like, this is how you should be doing, like independent set also. But then it's only one thing that if you are able to calculate the minimum vertex cover, then you'll be able to calculate the maximum independent set also, because I told you both are at complement of each other. Okay, so if that's, for example, if you are getting here A as a minimum vertex cover, then A complement, okay, will be the maximum independent set. Are you getting me? So if one of the
Yes.
two, if you are able to do that, I guess the minimum vertex cover, at least there is some method. Some method, I mean, you can just start with the maximum, the vertex which has the highest degree, and then you can just go ahead with the vertex which has what? Highest number of uncovered edges, right? You can go to that vertices which has the number of uncovered edges. You understand that, right? Uncovered edges means till now that has not been covered. Okay, with that vertices, that edge has not been touched out. Okay, so you can go with that vertices where there is a highest number of uncovered edges are left. Okay, and you can just repeat it out. This can be a one method to go ahead to calculate the minimum vertex cover. I'll give you one example more, and you try to calculate that. And you have to calculate the maximum independent set also, and both. Yeah. Tell me.
We have to cover all the edges, or we have to cover all the vertices?
You'll have to cover all the edges. If so, I told you an example, right? The camera example. You have to go to each and every corner. Okay, so you have to cover all the edges of the graph. See, if you have been something like that, A and B. So if you're just taking A, that is also fine, right? Because everything has been covered. If you're taking B also, that is also fine because this edge has been covered. So no problem in that. Okay. So now the next example is.
Above case, all edges were not.
In the above case, what happened?
I wonder, in above case, we can cover all the vertices, but there are missing edges. So it is not possible in this.
Sir, according to your second the definition that you wrote over this, second part, the H, if H is taken, then B, D, E, and G will not be taken. Am I correct? It is F.
Where I have defined something like that?
No, you said right now that once you take a edge, once you take a vertices and the edge connected to that, and the vertices
I
connecting
didn't say
to
that. I didn't say I didn't say that. Are you talking about this example?
Where you consider one vertices, then you leave the vertices that is connected to it.
No. That's not the case. I told you if you're just taking AB also, that also is a vertex cover. That's not a minimum vertex cover. If you're just taking A, that's a minimum vertex cover. Okay, but you're just mixing the independent set concept. Independent set is a different thing. In the independent set, whatever the set that you are making, okay, there should not be any value that should be like you can't take any adjacent vertex in that because that will make a edge. In the independent set, we have to take out all those vertices that can't make any edges. Okay.
Yeah. Okay.
Yeah. So let's try to solve it. Yeah.
Sir, for the method that we have to follow is same for directed and undirected graphs. Right?
For directed graph, the method will be same, but same I guess the method will be same, but again there won't be any direct like degree or something. You'll have to carefully have to do that for the directed, but the directed is not been discussed for us. Okay, at least for the minimum vertex cover, but you can solve it out if you have been given the directed also. You can do it, yeah, with the same method. You have to, but carefully you have to do it. Here there is no direction,
incoming
so
and outcoming we have to see.
You'll have to check that. All those cases you have to check.
Okay.
Yeah. So whenever we'll discuss the BFH, then there we can get an idea about the what happens whenever, what's the difference basically for undirected and directed. Whenever we'll start building the trees and all, so that can help. So I'll just give you one example. You have to solve it out. You have to tell me the minimum vertex cover, and if you are able to find the minimum vertex cover, you can find the maximum independent set also. So I guess now this is clear, right? Both of the term is clear to you. Are you able? You got it right. Yes, minimum vertex cover. You just have to make those vertices, those set of vertices you have to choose out that will cover all the edges. For the maximum independent set, you have to choose out all those maximum number of the cardinality of that the set that you are making should be maximum, but there should not be making any edges. Okay, there should not be any edges that they'll be making all those vertices that you are choosing out. Okay, those both are complement of each other. So if you are able to find one thing, you'll be able to find the other thing also. And there is nothing called unique. You can't get unique answer. If you are starting from one vertices, you can get a different answers also. Okay, so let's try to do this.
So then in the exam, like how will it will be asked? Like you're saying that there will not be any unique answer.
But if you're giving you, there can be a
There will be
MSQ
the
type of
choices
question.
will be in such a way that we'll be able to select as many possible
Correct.
possible
So
options.
so that
Okay.
becomes a difficult question. It's altogether. So you'll be having one question from. So whatever the topic that I told you, minimum coloring, there will be one question, and there will be one question from this topic also. The independent set, maximum independent set, or minimum vertex cover. Okay, and if that is in the form of MSQ, that becomes a very difficult problem, because you'll have to choose out all those options that can. Even from the option, you can make it like you can just choose out. Okay, these are the options, and then from those vertices you can just cut it out in the like all those edges which have been covered. And if you are able to find that from those options itself, so then it becomes simple from the options to choose out which can cover all the edges. That will be simple to solve that. Okay.
So
okay,
what can be the
you.
maximum degree that can be asked in the question?
Degree mean what, like the graph figure, or what you're talking? Degree. Okay.
Total connection available.
That
Total
won't
possible.
be full. That can't be more
If it
than
is like
3, 4.
complex 10, 15, then it will consume a lot of time.
No, that won't be that difficult. That will be like very simple, or like maximum quadrilateral, or that won't be that difficult. 4, 5 maximum.
Okay.
The vertex can be maximum 5, 6. Okay. Not more than that. Okay, so what I was talking about, one question that I was writing here is, now you have to tell me, these are all undirected graph. You have to tell me the minimum vertex cover and the maximum independent set. There can be anything, like you just tell me. I'll just try to think, like we'll discuss all those options that you'll be telling for minimum vertex cover or maximum independent set. So for this example, if I'm just writing A equals to 1 and 3, is this an independent set? Is this an independent set? Can you hear me?
Yes.
Yes, sir.
Yes, sir, it is.
Yes, sir. It is independent.
Is it a maximum independent set? No, right? Because you can have
No.
a bigger.
Yes, sir. We can add 5 and other.
6
Correct.
can be.
No.
Correct.
Okay.
Okay. So now you have got the idea. So let's try to solve this.
For independent set, we are checking maximum, and for vertex cover, we are checking minimum.
Correct. Maximum all those vertices that you can't make any edges, and here you have to choose out all those vertices such that the minimum number of vertices such that you can cover all the graphs.
For the minimum vertex, we can go in this way: 8, 3, 5, 7, 2.
8, 7, 5, 8.
Yeah, you can 8, 3, 5, 7, 2.
5.
Actually, there are many ways to do this, but
But I guess this is a vertex cover, but I don't think so. This is a minimum vertex cover. No, you'll be getting the vertex, the number as 4. Yeah.
8,
so
4, 7, 2.
This is one. See, I'm just clarifying once again. This can be your vertex cover. That is fine. You can cover all the edges with this one. But I'm asking the optimized version, the minimum. So the cardinality should be minimum for the minimum vertex cover. Okay. So if you are getting 3 with 3, so that becomes a minimum. Like that becomes the best optimized value. If you are getting 4, that becomes the best. If you have 5 and somebody is getting 3, that then the one with the 3 is the correct answer. Okay, not the with the 5. This can be a vertex cover, that I'm not denying. But is it the optimized version? That is what I'm talking about. I need the optimized version. Like what can be the number of that? Tell me the cardinality at least.
I'm getting 4, sir.
4.
Cardinality is 4.
So getting 5, sir.
5.
5. Okay,
And
let's
how
solve
four?
it out.
I tried, but how 4?
Okay, let's solve it. I have also not solved this. Let's try it out. So we'll start with what we have solved. We start with the vertex with the maximum edge. Which of them is the vertex with the maximum edge?
8.
8.
8.
Okay, so let's start with that. 8. If I'm just taking 8, what all we can exclude? I'll just solve this. Okay. If I just okay, so I just can remove this. This will be covered. This will be done. This will be done. Okay. What's the next part?
7.
The next
2,
is what
7,
did I
4.
say? You'll have to go with that vertices that has the maximum number of uncovered edge. Okay. Let's go with the 7. 7 ka, both of them are uncovered. Okay. Let's go with
Uncovered.
7. So if you're going with
7
7 to 7, that means this both are covered. What can be the next one?
2, sir. 2 is 4.
4 and
If
2.
I'm going with
4
4,
and 2.
no, then what about this 5, 6 line? This
Yeah,
will be
yeah.
left, right?
Yeah, that is the thing now.
Yeah, that is a 5.
Anyhow, like we are getting 5 only.
Okay. Okay.
5
Let's start
cardinality.
with.
What if
Let's
we
start.
choose 1, 3?
Okay. Let's start with 1. 1 as starting. So what all will be cut down?
Now, like from 1, but 8 is the vertex, right?
Sir,
Just
but
when
you
we
said,
supply
sir,
the
that
vertex.
CCTV
Yeah.
camera problem, sir, that one vertex is just able to see other vertex. So if from 8 also we can see 6, from 7 also we can see 6. And
No,
from this
but
4, this 5
5,
is
6,
covered
this
from 4.
5,
Cover the
6, this
edges.
lane you can't see. 5, 6 lane you can't see. Edges you have to cover. Okay, not vertices. In the
Yeah.
starting, what did I say? Edges you have to cover, not the vertices. If the vertices has to be covered, then it was fine. Whatever you said, 4 only. But edges, I said, right? Minimum vertex cover is what? You have to choose out all those vertices. With that, vertices will be covering all the edges of the graph, not the vertices. Okay?
Okay.
Got it?
Okay. Okay. Yes.
Let's start. Okay, and one more thing. I told you that can be one of the method to solve that. That's not the only method to solve the minimum vertex cover. Okay, this can be one of the method to solve the question. This is not the only method. That's why I told you. Because if there was some fixed method, then every time you'll get the unique value, right? Unique answer. This is not the only method to solve this question, this type of problem. You can start with if you are getting if you are getting 5 values, right? See, this is difficult. I can understand that. How can I because whatever the method I told you that was working for one method, but here you will see that won't work here. So here, if I'm starting with 1, so which of the edges will be visited from 1? 1, this is done, right? This will be done. This will be done, correct? What else? What is the next one?
6, 5,
5 we can take.
6, 5, 3.
Yeah.
Okay. So can I take, this is done, this is done, this is done. Can I take 3 now? If I'm taking 3, this will be done, this will be done, this will be done. Correct?
Yes. Yeah, correct, sir.
Okay. What about next I'm taking 5. If
5
I'm
and
taking
6.
5,
Yes.
5 I'm taking, this is done, this is done, this is done.
And
No, I'll take 7. 6 or 7, anything you can take. 7.
And 4 is also done, sir.
4 where? If I'm taking 5, this is done, right?
Yeah, yeah.
5,
You
I'm
said
taking
for
7
now.
now. So
Yeah, now it is 4. Now it is 4.
Correct? So now
Yes,
you
sir,
see
correct,
that
sir.
this is the minimum vertex cover. Now tell me the maximum independent set.
It's
Maximum
wrong.
independent. Is it
It's
wrong?
wrong. 6 to 8 is not taken in this.
In 7, it is not connected to.
7 is not right. It should be 6.
Rather than taking 7, you should take 6, sir.
Yes, sir. We
Okay,
should
okay.
take 6 only.
Yeah, correct. I should be taking 6. If I'm taking 6 now, okay, now it is covered, right? Okay.
Yes. Now it is covering.
I'll just put it here. Let's write it again because that was a confusing. I started with 1. So this is done, this is done, this is done. Next is 3 I took, right? This is clear, then done. Next I took it 5. 5 I'm taking, this is done. Correct?
Yeah.
6 I'm taking next. So
Yes.
this is clear. Correct? So this should be the minimum vertex cover. Correct? Yeah.
Correct.
Yes,
What about the maximum independent set? Now can you tell me the maximum independent set? I told you A complement, correct? Now what's the
2,
A
4,
complement?
7, 8, sir.
2, 4,
7, 8.
Is this the maximum? You can just check it out. Are you able to make any edges from 2, 4, 7, 8? And that is the maximum independent set also. Is this clear to everyone? So if any of the two, if you are able to, like for example, if somebody is like finding simple to calculate the maximum independent set, then you can directly calculate the minimum vertex cover from taking the complement. If you are able to calculate, yeah.
Can we go with this with like 1, 4, 6?
Okay, only 3 for minimum vertex cover. Huh?
Yeah, for that. No, I'm not sure you can you
No,
just
yeah.
clarify?
You told
1, 4, and 6.
7, right? So 1, 6 I'm taking 6. So if I'm taking 6,
we can't go. No, we can't go in that way. 2 and 3 is not being covered that age.
yeah. 1, 6 and what did you say? 1, 6, 4.
1, 4, 6. Yeah, it can cover. No, it can cover.
No, this will not be covered, right?
2,
This
3,
age
5,
is
8
not
is not covered.
This is
No,
also
but
not covered.
no. For that, vertex 1, maximum vertex set 1.
Maximum
She's talking about
vertex.
independent.
Maximum
Independent set.
Independent, yeah, independent.
So maximum independent that you're talking about. But that is not
Set
maximum
that
itself because you're just
number of elements.
maximum independent set should be having maximum number of elements.
Maximum number of
1 to
elements.
I told you, right? 2, 4, 7, 8. You have given me 3, right? 3 can be. I'm not denying that. That can be one of the independent set. I'm not denying that.
Sir, I will
is
give
it
you
the
an
maximum?
independent. I will give you an independent set of cardinality 2. Just take 2 and 8. But that
can
will not.
Be
Yes,
yeah, that
but that is not
can be
maximum.
independent, but that's not maximum.
Yeah, I was confused between these two concepts. Sorry.
No, so I am telling you again and again, independent set will have to find out the maximum cardinality for independent set, such that none of them would be making an edges. For minimum vertex cover, that the word itself telling you that you have to pick out the minimum number of vertex. The cardinality should be minimum. Okay, such that it should be covering all the edges of the graph. Yeah.
Sir, in this example, for minimum cover, we have to take the vertex which has maximum degree. But here, if we take 8, we are not able to come up with the solution, no?
One more thing. The method that I told you, that's one of the method to solve this. That's not the only method. Okay. So if you are not getting any idea, you can start with that approach. Okay. But so we were solving that approach. We were getting 5 as a vertex, right? The cardinality was 5. But we went to some other method. We found it. Not the method, but basically we randomly pick out some of the vertices. We have started with 1, and then we found out that we are able to find the minimum, like the lesser cardinality than the other one. Okay, then that becomes the optimum value, optimum minimum vertex cover. Is this clear to everyone? If you have any doubt from today's session, you can just ask me. The remaining portion will start with maybe one more session. We'll be doing it for this week, and because that has a lot of concept, so you can just ask me whatever we have discussed it today. Okay, and the
Sir,
remaining maybe I'll put it one more session tomorrow, and then we'll deal with the other portion that has been left. Yeah, go ahead.
Sir, I have a doubt, sir. Sir, in this
Yeah.
vertex cover, we were checking the minimum cardinality, and for this independent set, we are checking maximum cardinality. Is it possible that vertex cover cardinality will be more than independent set cardinality? Because in this question, we got the cardinality same.
See, it can be more. It can be more. There is no problem in that. There can be more. You can take. See, I was giving one example. One example itself. AB. Okay. If you have to just take out the pull out the vertices with such that this simple graph, you just have to pull out those vertices such that the whole edges have been covered. What can you say? Which of the following vertices? Like you can take AB also, right? You can take A also. You can take B also. All these three are correct. If I'm just asking you, you just have to pull out all those vertices such that the whole edges has been covered. These three are correct, but I'm asking you to optimize this. You'll have to find out the minimum number of vertices. So this and both are correct, right? Are we getting any unique answer? No, right? Because if somebody starting with A, will be getting A only as a vertex. If somebody is starting with B, will be getting B as a. So we are not getting any unique answer, right? So I told you, right, for the minimum vertex, you will not be getting any unique answer. Okay, even for the maximum independent set also, you will not be getting any unique answer. Okay, you can get a different sets. Okay, but you have to optimize and get so the cardinality should be minimum for the minimum vertex cover, and for the maximum independent set, the cardinality of that set that you are creating should be maximum. Okay. See,
so sir, what will be the independent set of this graph you created just now?
For this graph?
Yes, sir. Independent set.
Independent set A can be your independent set, right? If you're writing AB, that is not an independent set. Because AB, if you're just taking, both will make an edge, right? I have to take out all those vertices so that it should not be making any edges. There should not be any edges between them. So A can be one of, B can be one.
So it became same only cardinality of independent set and cardinality of this vertex cover became same.
If this is your minimum vertex cover, you are taking complement. If you take complement, what becomes B? B is your maximum independent set. Correct? And if you're taking B as a minimum vertex cover, the complement is what? A. That's the maximum independent set. And this is a maximum independent set. You can't take more than one. You can have only one, right? So that you will not be making any edges. Because you can't take this because that will make an edge.
Sir, this notes will be shared in the course introduction. Supplemental content.
Notes is not okay. I'll just write it out again and then I can say, because this is like messed up.
Okay. Can you just show the index alone initially? First page alone.
Yeah, this.
So where you listed all the
topics. This was the index. So we have done.
We are done with this note and
what?
save this in the chat. It would be better for us.
But this is messed up. Like, I don't think we'll be able to understand it from here. I can write it and then can be shared. Okay, after finishing the whole, the remaining questions, I'll be writing it out and then share with you. Okay, in the supplementary content.
Okay, sir. Okay.
Then it will be better.
Sir, I've got a doubt.
Yeah, anybody? Yeah.
Is there any good textbook on this topics?
Textbook. Have you gone through our whichever?
Yes, I did, but that's not comprehensive, or it is not elaborating many things. It summarizes certain things.
It is summarizes. Yeah, I can come up on maybe tomorrow and I'll let you know about. Okay, for sure. Yeah. Thanks.
Sir, I've got a doubt in adjacency matrix.
Adjacency matrix. Okay. Go ahead.
Sir. So in that you've mentioned that A then vertex 1J. So it means from vertex 1 to J, we can also infer it as J to I. I mean I to J or only J to I?
Only I to J. If there is an undirected, if there is a directed one, you already know that. See, adjacency of I to J. If you have a graph that is basically undirected. Okay, undirected, that means bidirectional. So if you have an adjacency matrix, I to J have been given to you, you already know that J to I also there will be a connection, because that's a bidirectional, correct?
Yes, sir.
Okay, so if you have a bidirectional, that means what? I to J and J to I, both are the edges, right? Both have the relation. if you have a flight from I to J, there must be J to I also that will flight, because that's an undirected or a bidirectional plot, right? So for both the cases, it will be 1. Are you getting me? But it has been defined in this case because it will work for both directed and undirected both.
So actually, my doubt is a bit different. My doubt is that when we write A, then in square brackets we are writing I comma J. So it
This is
refers to
basically
I
I
to
to J.
J, or
Yeah,
it
this
can also
refers
refer
to
to J to I.
No, it just refers to I to J. If it has been written something like that, J to I, then you can say that J to I there is a connection, there is a relation. You can't say I to J. It just said that J to I. If you have written in this way, I to J, that means I to J only. Nothing J to I, no. Okay? So that's why it
Right.
says, right, it equals to 1 if there is a IJ belongs to the edge. If there is a relation between I and J. If there is a relation, then only that becomes a edge, right? If you don't have, then that's not a edge. Okay?
Okay, got it. Thank you, sir.
Okay, thanks. Any
Sir,
other
I
problem?
have a doubt that over here it is written that I to J equals to 1. So basically, we are going from I to J. If it is true, then we are giving 1, or else.
Correct. Nothing.
If it
there
is
is
false,
no,
then it is 0,
0.
right?
Yeah, you can see that, right? If there is a connection from 3 to 4, you're writing it 3 to 4. Okay, that means 1. Correct? Is there any, so
Yeah.
from 3, can you go anywhere else except 4? No, because there is no connection from
the
3 to
direction
2.
is
There is
1 to 3. So
yeah,
we can't go
1 to 3, correct. So 1 to 3 is there, so that's why 1. But 3 to 1, there is no connection, right? If it was like this bidirectional, then you would have written 3 to 1 also as a 1. Okay, I hope this is clear.
Yes, sir, this is clear.
Sir, on the
Yeah.
very last page, the graph that you made, like from A to B, the maximum index set, like cardinality of the maximum index set was just 1, right? Yeah, here.
Yeah, it will be 1. Maximum independent set, right? This is what you're talking.
Independent.
That will be 1.
We can't take this like A, B, like both.
You can't take, because that will make a edge, right? Independent set is what I have defined you right here. Independent set where this has been defined. Subset of B such that no two, whatever the edges, the vertices that you are taking, in that vertex such that no two vertices are connected by an edges. If you are taking A, B, that means what? It will make an edge, right? That should not make an edge. So you have to take out all those vertices that will be basically from the original vertex set V, such that no two vertices that are there in your set that you have made are connected by the edges. Okay?
Yeah, got it. Thank you.
Okay. Anyone has any other issues till now? So we have dealt till adjacency matrix. We'll be dealing with the BFS, DFS, and directed cyclic graph and topological sorting. That will take some 1-2 hours again. So yeah, maybe tomorrow or day after that we'll check. Tomorrow or day after that, I'll fix one schedule, because Friday you have a session morning. Maybe Thursday I'll put it, or maybe tomorrow I'll just see that whether I have any other session or not. Okay. So you'll get to know by tomorrow morning.
Sir, like whatever you've taught today, if you can just put it in a note form, it will be great, sir.
Yeah, I'll put it and share.
You can there is a Google sheet where all the things are maintained. Also, even if you give the link, it will be better there. Like, we can access it. Instead of you uploading it as a supplementary content, we can even that Google sheet, if it is available.
Okay. Google Sheets. Okay. TA. That sheet you're talking about.
Yes.
Okay. I'll that there also I'll put it, and the supplementary content also.
Because this will be very helpful for us to understand the topics.
Okay. So both places I'll upload it, and supplementary content also, and I'll share with the TAs also. They'll share it.
Okay. Thank you.
Okay. Thanks everyone. So we'll meet again for the remaining topics that needs to be discussed. Okay.
Thank you, sir.
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 Okay. Thanks.
Thank you,
everyone. Yeah.
Good night, sir. Good night, everyone.
Yeah. Good night. Good night, everyone. Yeah.
Good night, sir.
Thank you, sir.
Thanks everyone.
In my college also, sir, ma'am referred this book only for this graph theory and suggested this R. Balakrishnan book.
Okay, thanks. Okay, I just. Yeah, we can refer this. This is a nice book. Like all the concept, I guess, is already been given here. Coloring, matching.
But these concepts are not required for our course.
I'm looking for some algorithms. That's all.
Very deep concepts. I think in this book only I came across this 7-bridge problem. It was interesting.
Very old problem.
Yeah, that's very old problem.
That is a foundation for the graph theory.
Sir, which book is this?
Bhaskaran sir, have you read this book completely?
You can download it.
Sorry, sir.
I've given the link. You can download it.
Okay, sir. Okay. Thank you, sir.
Yeah, sir. Thank you for reading. And thank you, sir.
Thanks for the book. Thank you, everyone. I'll just drop it.
Thank you.
Thank you, sir. Thank you.
Thank you. Good night, Bhaskaran sir.